Welcome, friends, to this session. We shall be looking at Senior 3 work, that is Chapter 3, Formulae, Stoichiometry, and More Concept. And as we go through this chapter, I want to request those who have not yet subscribed to go back on the channel. We subscribe and also click on the notification button that you shall always get the updates and other upcoming tutorials in regard to chemistry. So as we begin on this topic, this is our very first lesson that we are looking at. In this topic, we shall be starting with relative atomic mass of an element and the relative molecular mass. And we shall begin from what an atom is. What do we know about an atom? We know that an atom is very tiny, very small, and therefore it is very impossible to determine its mass by weighing. You can do the weighing of the sugar, you calculate the weight of sugar in kilograms, but we're saying that because an atom is very small, we can't determine its mass by just mere weighing. So what do we do to get the atomic mass of an element? What do we do to get the relative atomic mass of an element? Relative molecular mass. So those are the things that we want to first look at, to dive into and understand how best this is calculated and determined. So we're saying that the atoms of different elements, they have different atomic masses. We have atoms of sodium, atoms of magnesium, atoms of calcium, and we're saying that each element has its atomic mass. And we're saying that the atomic masses of the elements are obtained by comparing them with the mass of carbon 12. This was done some time back, long time ago, when this discovery came about, and they found out that carbon 12 could be one of the things they could compare because its mass was very well known at then. So we say all the atomic masses of the elements are obtained by comparing them with the mass of the carbon 12. When you say mass of carbon 12, this is carbon, the isotope of carbon with mass number or atomic mass of 12. So this is the way that we write isotope of different elements, and this is the one of the isotopes of carbon, which is carbon 12. So saying that the relative atomic mass of an element is the average mass of isotopes of element compared to 1/12 the mass of one atom of carbon. So this is how we can define atomic mass of any given element. And we're saying that we can summarize it in this formula where we're saying that relative atomic mass, or abbreviated as RAM, is equivalent to the mass of an atom of an element, then divided by 1/12 of the mass of one atom of carbon 12. And we say the mass of one atom of carbon, its mass is 12. So 12 of this, which is 1/12 times 12, which means you get a 1. We shall be able to see how we can calculate that. So we're saying NB, that IUPAC, which is International Union of Pure and Applied Chemistry, recommends carbon 12 atoms to be the scale. So this is something which has been agreed internationally. So a group of people came together and had to agree on which thing they could use to be the scale, and using this the IUPAC system is the one that recommends the carbon 12 to be the scales. So even when we are getting the relative atomic mass, we can see comparing it with the mass of carbon 12. So in this, we are saying that the mass of carbon atom is taken to be 12 atomic mass units. the 12 atomic mass units. So we have summarized it as AMU. So whenever we see AMU, just know we are meaning the atomic mass units. So 1/12, the mass of carbon atom is 1. I believe we know very well when we say 1/12, that is 1 out of 12. So if you say 1 out of 12, this is 1 out of the 12, and then times, when we say times 12, times 12, which means this 12, it will cancel by 12 1, by 12 1, and you can see our answer becomes 1. So that's why we're saying that the mass of carbon 12 is taken to be 12 atomic mass units. So when we talk about 1/12, the mass of carbon atom, that's why we're saying it is 1. It is 1. So that is the mass of carbon 12. Okay, so let's look at this. We're saying that relative atomic mass has no units. When you look at this formula here, it is mass of an atom of an element over still the mass. Why? Mass is measured in grams, and also down here we see mass of carbon 12, which is still in grams. So when you have grams over gram, the grams will cancel. And finally, we find that it doesn't have any units because it is a ratio. It is a ratio of mass to mass, and therefore the units cancel. And finally, we may not have any unit of RAM. So we're saying that we can use the periodic table to get the relative atomic mass of different elements. So when you get any periodic table that we have, and you check on the periodic table always has the symbols of an element, the atomic numbers, and atomic mass of different elements. So when you use that one, we shall be able, we have already seen that a 12th of one atom of carbon 12, of the mass of one atom of carbon 12 is equal to 1, which means at the end of it all, when you're getting relative atomic mass of any element, just get its mass, which we get from the periodic table, and then we divide by 1. So when we go on the periodic table, this is a table that we want to use to determine the relative atomic mass of some elements. The first element we want to talk about is hydrogen with the symbol H. When you go on the periodic table, we find out that its mass is 1. When you substitute in our formula where we said it is mass of an atom, so the mass of hydrogen, which is 1, we divide by 1/12. 1 over 12, which we have seen here, times the mass of one atom of carbon times 12, which means we'll be able to get 1. So this over is always 1. So the mass you get on the periodic table, it will become that mass of 1. Don't forget, for the relative atomic mass, it has no units. That's the difference between the relative atomic mass and the molar mass of a given element. Relative atomic mass doesn't have units, while the molar mass of a given element, it has units. So that's where we have the difference. So when you look at carbon, its mass is 12. So which means even its relative atomic mass remains as 12. Then for oxygen, when you check on the periodic table, you find that its atomic mass is 16. So 16 divided by 1, we get still 16. So in this case, you find out that the difference is that for this, it doesn't have any units. And the same case we do for sodium. And so sodium, we have 23. Divide by 1, and still we get the 23. Then we have magnesium, which is also having atomic mass of 24, and therefore its relative atomic mass becomes 24. So in this this was just a sample of some elements. We can try out any other element on the periodic table. So when you go on the periodic table and you find the different elements, their mass numbers is equivalent to their relative atomic mass. The difference is that for relative atomic mass, it doesn't have any units. Why? Because if you look at this formula of determining relative atomic mass, where we're comparing the mass of an element we compare it to that of carbon-12. So when compared to that of carbon-12, it is mass over mass, and therefore the units cancel out and we don't have any unit of the relative atomic mass. So that is how we can calculate the relative atomic mass of any given element. Let's look at relative molecular mass. In relative molecular mass, we are saying that the relative molecular mass of a compound is the average mass of isotopes of the compound. So the difference we can see here, it is of the compound. We are looking at the molecular mass. So in this case, we are saying that the relative molecular mass of a compound is the average mass of isotopes of compound compared to 1/12 of the mass of one atom of carbon-12. When you look at the difference between this atomic mass, it is the average mass of isotopes of element. It is of an element, that is for atomic mass. But when you talk about relative molecular mass, we are talking about a molecule. So a molecular mass, it is having different, more than one element in one compound. So it is a compound, not one element. So we're saying also the relative molecular mass has no units. Why? Because it is a ratio. It has no units because it is a ratio. Okay, let's see. We're saying that in the relative molecular mass of a substance is the mass of 1 mole of a molecule of that substance. The relative molecular mass of a substance is the mass of 1 mole. So which means 1 mole of a substance of a molecule is equal to its relative molecular mass. When you have calculated the molecular mass of a given substance, then you know what 1 mole weighs in terms of mass. We are going to see that as we continue to dive into the relative molecular mass. So I'm saying that relative formula mass, now we may get confused, the relative formula and relative molecular. So we use relative molecular mass for substances which mostly for covalent. We also use having only non-metals. For example, carbon dioxide, like ammonium, like oxygen molecule. Those ones which are having the what? Only non-metals. Now, whenever we have a compound which is like ionic, so having a metal and a non-metal, then there we use relative formula mass. So RFM and RMM should not disturb us. In this case, looking at sodium hydroxide. It is sodium. Sodium is a metal, and these ones are non-metal. So whenever we have such, we call that one the relative formula mass. So I'm saying that relative formula mass of sodium hydroxide pellets is 40. We shall see how they got 40. This means that 1 mole of sodium hydroxide has a mass of 40. Therefore, its molar mass is 40 grams. I'm saying the difference. Molar mass is 40 grams. But when you talk about relative formula mass, is 40. The relative formula mass has no units, but molar mass has units. So that is the difference. Let's see how we can calculate the relative molecular mass, or how we can calculate we can still say how we can calculate the reactive formula mass. The reactive formula mass. We say that this one is for ionic compounds. This one is working for covalent compounds. So when it is covalent compound, we use reactive molecular mass. If it is ionic compound, we use reactive formula mass. I believe that is very clear. Let's see, how can we calculate the reactive molecular mass of a given substance? Okay, let's look at that. How do we calculate the reactive molecular mass of a substance? So in this case, we are saying that the reactive molecular mass of a substance is obtained by adding up the reactive atomic masses. I believe if you recall very well, we talked about this. The reactive atomic mass, we get it from the periodic table. And when you go on the periodic table, we make sure that we choose the molar mass of a given substance, but now we don't consider putting the units. It doesn't have units. Why? Because it is a ratio. Let's look at, let's consider this periodic table. We can get a periodic table here online. We can get one periodic table. Let's search one periodic table, and then we see periodic table. If you don't have a periodic table, you can search one online, and then we can see what, and you have your own copy. You have your own copy. So we have, let's have this periodic table, and then we look at how we can always refer to it when you talk about good. So we are seeing that when you have this periodic table, it will be able to give us the different molar mass of a given element, and also to give us atomic number. But in this case, we are looking at molar mass. So when you come on this periodic table, you have like boron. Its atomic number is 5, molar mass is down here. When you check here, its molar mass is here. So any periodic table you have, you always find there the atomic number and the molar mass of that substance, of that element. So for hydrogen, it is 1, and down here it is 1.00, but we consider the 1. Let's look at the one for carbon. Carbon, it has atomic number 6, but mass number of 12. So when you have a periodic table, you'll be able to get the atomic mass of different elements. Then for you to say it is reactive atomic mass, just don't put units, because we say that for reactive atomic mass of any given element, it doesn't have units because it is a ratio. Okay, so let's come back here that the reactive molecular mass is obtained by adding up the reactive atomic masses of all the atoms in the formula of a substance. So calculating the reactive molecular mass of a compound is done in 2 steps. Which steps are we talking about here? So we have these 2 steps. Number 1, write the correct chemical symbol of the compound. So when we are calculating the reactive molecular mass of any given compound, the first thing is to write the correct chemical symbol. Then number 2, we sum up the atomic masses of elements present in that given compound. Let's have an example to try out. So in the first example, we are saying calculate the reactive molecular mass of magnesium hydroxide. So magnesium hydroxide, it consists of hydrogen atom, it consists of oxygen atom, it consists of magnesium atom. So they have already given us their atomic masses. Atomic mass of hydrogen is 1, Atomic mass of oxygen is 16. Atomic mass of magnesium is 24. Where do we get these atomic masses? We said you just get them from the periodic table. If you don't have a periodic table, just download, go on internet and do what we have already done. Download your own copy and you always use that. So for this case, we have already put these atomic masses into in the question here. So we say that there are only two steps: writing the correct chemical symbol. The word is correct, making sure that you write the correct chemical symbol of the compound. And then after that, we sum up the atomic masses of elements present in the compound. So let's look at magnesium hydroxide. So the first step is to write the formula of magnesium hydroxide. We know magnesium hydroxide consists of magnesium and then the hydroxide. So what we do is to put the valence. We assign the valence of this of magnesium. So the valence of magnesium is 2. That's why we see a 2 here. And then assign the valence of hydroxide, which is a 1. After assigning the valence, then what we do is to interchange. We interchange these valences. The one for magnesium, we put it on the hydroxide, and then the one which is on hydroxide, we interchange it, comes to magnesium. So at the end of it all, we have the formula of the compound of magnesium hydroxide as Mg and then OH, then with a 2. This 2 is coming from the magnesium. So where do we get these valences? I believe in senior 2, we are able to look at the valences, how to write valences of different elements, writing valences of different radicals, like hydroxide, sulfates, but in this case we have the hydroxide. So after writing the correct chemical symbol of the compound, in this case we can interpret this by saying that magnesium hydroxide is made up of 1 atom of magnesium, 2 atoms of oxygen, and 2 atoms of hydrogen. These 2 here affects all these inside the bracket, which means that there are 2 atoms of hydrogen, 2 atoms of oxygen, and then we have 1 atom of magnesium. Then we can go to step number 2. So step 2 is adding the relative atomic mass of the elements in this compound, summing up. So we have already seen that we have 1 atom of magnesium, and we already know its atomic mass. So what we do is come and we sum up atomic masses of these elements. So we're saying that magnesium, it is 1 times its atomic mass, which is 24, plus oxygen, we have 2 from this formula. There is a 2 outside here, so which is affecting this oxygen. Therefore, there are 2 oxygen atoms. So we say 2 times the atomic mass of oxygen, which is 16. Where do you get this one? You can get it from the periodic table. Then we come to hydrogen. Hydrogen also, this is affecting it. Therefore, there are 2 atoms of hydrogen. So we come and say 2, which is 2 atoms of hydrogen, times 1, which is atomic mass of hydrogen. What is 1 times 24? We get 24. 2 times 16, we get 32. 2 times 1, we get a 2. So when you sum up 24 plus 32 plus a 2, I believe we are able to get a 58. We are able to get a 58, and therefore we can conclude by saying the relative formula mass of magnesium hydroxide is 58. Relative formula mass of magnesium hydroxide is 58. So we are saying that we are not putting any units because we say that the relative formula mass, relative molecular mass is a ratio. Therefore, we don't need to put units. Please don't forget to subscribe, like, and comment and share, such that very many other people can always benefit from what we are learning. And when you appreciate also what you're getting, don't put a thumbs up somewhere, and so that we know that you people are following. These are practice questions. I want us also to practice. Practice questions. Calculate the relative molecular mass of the following compounds. Part A, ammonia. Part B, water. Part C, calcium carbonate. I want you to follow the steps, the 2 steps we have looked at up there, and we get the answers for this. Part A, ammonia. Part B, water. Part C, calcium carbonate. Now, it doesn't matter which class you're in, whether in senior 1, senior 2, senior 3, senior 4, or any other person that is going through this work. Make sure that you pause, go back and check on what you have already discussed, and you try out these questions. When you get the answers, share them in the comment, and we find out. So you say ammonia, its relative molecular mass is this. Water, its molecular mass is this, such that we can know that you're following, but also understanding the concept. So I'll be waiting to see the answers to that. So we have been able to share how we can calculate the relative atomic mass and relative molecular mass, or what we are calling the relative formula mass. The difference between the relative molecular mass and relative formula mass is just that for relative molecular mass is for a covalent compound, while relative atomic mass is for the ionic compound. Let's dive into a mole. You know, a mole, this is something that disturbs some people, but today we are going to see what a mole is. Don't forget, this is the topic we are looking at: mole concept, stoichiometry, and formulae. And I believe in this session we shall be able to cover a half of this topic, and our next session we shall be looking at how to complete this full topic together. And whenever you get any query, any question, always ask in the comment sections. We are always there to respond to our questions. Now let's look at a mole. A mole is the amount of a substance which contains as many particles as 12 grams of carbon-12. Now, someone may start asking, what is all this? What are you talking about? What is a mole? Let's first look here. There's something I put. Look here. In daily usage of items, every day, I believe every day, each one of us, we use different items. We count them in pairs, in dozens, and so on. For example, here I have some examples. How do we count the eggs? Eggs, we count them in trays. You see, we count how many trays of eggs are you going to take. Soap, we count it in bars. When you go in the shop, you say, I need a bar of soap. When you go to buy shoes, I need a pair of shoes. You see, this is how we do count things in our day-to-day life. Sugar, go in the shop, I need half kilo. It is measured, it is counted in kilograms. Sodas, counted in crates or cartons. Books is counted in dozens. Now, we're saying that when you look similarly, for chemists, they use a mole. Chemists use a mole as a unit to measure, a unit of measure for particles. The way we do count things in our day-to-day life, we count books in dozens, we count sodas in crates, we count sugar in kilograms. Similarly, we are saying for chemists, they use a mole as a unit of measure of particles. Now, a chemist wants to know how many particles. Maybe let's talk about like sodium chloride, the one we use every day for cooking food. Sodium chloride, that is the common salt, the table salt that we use for cooking every day. And it wants to know how many, it consists of sodium and chloride ion atoms, and wants to know how many sodium atoms are present in 500 grams of the packet of salt. Now, that is for them, they count this in terms of moles. And we are going to see how we can do calculations of moles in this subsection. So finally, we are saying that mole of a substance is the amount of that substance contains the same number of elementary entities or particles as the number of particles in exactly 12 grams of pure carbon 12. Don't forget that according to IUPAC is just when people came together from different places and then they said, let's agree upon what to use. So the IUPAC, International Union of Pure and Applied Chemistry, they sat down and said, let's always use carbon 12. This is the isotope of carbon, which is always used as the base, or that the one we use for comparing other elements. So I'm saying that a mole is a substance, or a mole of a substance is the amount of that substance that contains the same number of elementary entities or particles as the number of atoms in exactly 12 grams of pure carbon 12. And we're saying that the 1 mole of substance, 1 mole of substance contains approximately, this is approximately 6.02 times 10 to the power 23 particles. This huge number is called the Avogadro's constant, or what we call the Avogadro's number. So this is a constant number, Avogadro's number, and we're saying that 1 mole of a given substance is equivalent to this number of particles. Which means at the end of it all, we can be able to know how many particles are present in this sugar that I'm taking, how many particles are present in this, how many particles of this element is present in this sodium chloride that I'm eating. So all this is the reason why we need to learn a mole concept and we need to learn moles. Let's look at some of the conversions of number of moles and number of particles. We have seen here that 1 mole of a substance contains approximately these particles. So we want to see how we can convert different moles into particles and particles into moles. Okay. So I'm saying that the conversions are based on the equivalence of 6.02 times 10 to the power 23 particles. Now, these particles we're talking about, they can be the atoms, they can be the molecules, they can be the ions of a substance, and 1 mole of that substance. I believe that one now becomes clear. So when you talk about 1 mole of a substance contains approximately this number of particles, we are saying it can be this number of atoms, it can be this number of molecules, it can be this number of ions, but we are saying it's equivalent to 1 mole. So that is what we're going to be using in calculation and converting numbers of moles into particles and particles into moles. I want you to pay attention and also keep on pausing and you note down. So at the end of it all, when I give you practice question, you're able to go through it and test yourself whether you have gotten this concept or not. And whenever you get any question, any query, something you have not understood, make sure that you ask. Let's look at this example. This example is saying convert 1 times 10 to the power 23 atoms of sodium into moles of sodium atoms. So we want to convert these particles. We said the particles can be atoms, they can be molecules, they can be ions. So we want to convert these particles of sodium into moles. Are we there? Now there's something that we already know, that 1 mole of any given substance is equivalent or contains 6.02 times 10 to power 23. So that's why in the solution here we are starting with this. Since this, which is 6.02 times 10 to power 23 atoms of sodium are contained in 1 mole. You call this one, we got it from Avogadro's constant, that 1 mole of a given substance contains this number of particles. So we're saying that since these atoms of sodium contain 1 mole, okay, now what about these ones they have told us? If these atoms contain 1 mole, what about these? So which means we shall be having 1 over this which we have, then we multiply by 10 to power 20, 10 to power 23. Okay, so this one, I think we need to remove this. So it is 1, this should be 1 times 10. 1 times 10, so this 10 should be up here, 10 to power 20, 23, power 23. Then we divide by this. I believe we know this mathematics when we are saying that if these atoms of sodium contain 1 mole, are we there, of sodium atoms, and what about these atoms? Which means these atoms, we can say these atoms of sodium are contained in this. So we multiply by this over the other one, over the one which we had at first. So at the end of it all, when we get this one at 10 to power 23 is going to cancel. It will cancel with this. It will cancel with that. And then, which means we'll be having 1 over 6.02. You can put in your calculator and then we see whether you get 0.1661 moles of sodium atoms. So that will be our answer. We are converting particles into moles. So we have been able to convert these atoms into number of moles. So we can conclude and say, therefore, 0.1661 moles of sodium atoms contains these atoms of sodium. So it is now your task to look for more numbers, but I'll be able to give you another number for practice of seeing how you can convert moles into particles. We have seen how to convert particles into moles, and then you can practice converting moles into particles. I'll be able to give you some practice questions at the end of this lesson, and then you practice and check yourself whether you have gotten the point very well. Now, let's look at mole and molar mass. So when we talk about mole and molar mass, we want to see the relationship between the molar mass of a given substance and the mole. So here we're saying that the mass weighed by 1 mole of a compound or molecule is known as molar mass. The mass weighed. This is something that we need to note. Mass weighed by 1 mole of a compound or molecule is known as molar mass, which means 1 mole of any given substance is equivalent to its molar mass. That is something that we're going to be using very much, and therefore we need to get it very well, that the mass weighed by 1 mole of a compound or molecule is known as molar mass. So the relationship between moles and molar mass. Let's look at the relationship between moles and molar mass. So here I think the number in a given mass of an element can be calculated using the formula. The formula moles is equal to the given mass of an element divided by its relative atomic mass. So if you want to know the moles of a given substance, for example, the number of moles in 500 grams of sodium chloride, if you know the mass you have, you can put its mass, you divide by its relative atomic mass, and then you get to know the number of moles present in that sodium chloride. Let's have an example. This is just a formula, but we can also use the first principles. For example, here they're saying determine the number of moles of magnesium atoms, the number of moles of magnesium atoms in 22.3 grams of sodium. Oh, this is a mistake. So we're saying that determine the number of moles of, this should be of sodium. So we're saying that determine number of sodium atoms. Sodium. Sodium. So let's write it very well. Is that sodium? Okay, but I believe you can see it. So we're saying determine the number of moles of sodium atoms in 2.3 grams of sodium. So and in our solution, we're saying that 23 grams, the 23 is the molar mass of sodium, because we have already seen that 1 mole of a given substance is equivalent to the relative molar molecular atomic mass of a given substance, or is equivalent to the relative molecular mass of a given substance. So we're saying that 23 grams, which is the molar mass of sodium, are contained in 1 mole of sodium atoms. If 23 grams contain this, what about 2.3 grams of sodium? So which means we say 2.3 grams of sodium contained in 1 times 2.3 divided by 23. So we divide by 23 both sides, and then we know what about this, which means we can multiply by 2.3 and we get 0.1 moles of sodium atom. So we have just, you can see this is, you can just substitute in this equation, or you can use the first principles. The second question is asking how many moles of iron atoms are there in 1.204 times 10 to power 22 atoms of ions. So in this case, they want us to see how many moles are there in these atoms. These are particles of iron, and they want us to find the moles present in these particles. So what do? We already know something, that from Avogadro's law, we say that these particles, 6.02 times 10 to the power 23 particles, and we say that particles can be atoms, molecules, or ions, and in this case, in this question, we are looking at the atoms. So these 6.02 times 10 to the power 23 atoms of iron are contained in 1 mole of iron atoms. Now what about this, which they have given us? So this will be it will be 1 over this times this, but only that it is down here. We shall be able to add it up. So it will be this divided by the other one, which is 6.02 times 10 to the power 23, and the answer we get 0.02 moles of iron atoms. So when you compute using your calculator, you see that you'll be able to get 0.02 moles of iron. Then part B is saying what is the mass of 1.202 times 1022 atoms of iron. Now they want us to determine the mass. We already have the number of moles. Now they want us to determine the what? the mass, but we have the formula. You can substitute in the formula, or you can use, if you check here, we already have the formula that we can use. You already have the moles, you already have the relative atomic mass. What they want is this mass. So you can look for this, or you can use this formula that we are going to use here. Let's look at it. So here on this, we're saying that 1 mole of iron atom weighs this. This is the mass of iron. If you check on the periodic table, you'll find there 55.80 grams. So 1 mole of iron, it weighs 55.80 grams. What about the 0.02 moles, which we have here? The 0.02 moles, it will be 0.02 times 55.80 grams, and we get 1.116 grams, and then you'll be able to get your answer right. Yeah, so that is how we can relate the moles with mass and moles with particles. So in this, what we have finished calculating, we can relate all those, the particles, the moles, and also the mass. So from there, I want us to also look at the last bit of this lesson, which is the moles of a gas and its volume. How do we relate the moles of a given gas and its volume? Now we are saying that the volume occupied by 1 mole of a gas at standard temperature and pressure. The volume occupied by 1 mole of a gas. Now here I'm saying of a gas, it is any gas, whether carbon dioxide, whether oxygen, whether nitrogen. The volume occupied by 1 mole of any gas at standard temperature and pressure is the one you call the molar gas volume. Is what you call the molar gas volume. And I'm saying that the molar gas volume varies with temperature and pressure. The molar gas volume varies with temperature and pressure. But there's one thing that we have known, that the volume occupied by 1 mole of a gas at standard temperature and pressure is called molar gas. But you're saying that the temperature and the pressure, they always do what? They always change. So let's look at this table. This table is showing us the volume of gas at various standard conditions. Now let's look at this table. I want to bring the full table here. I believe we can see it very well. Okay, there. So in the first column, we are showing the condition, the temperature, and the pressure. So the standard temperature and pressure, which you call the STP, its temperature is 0 degrees Celsius, and pressure, which is 750.06 millimeter per mercury. Then we also have room temperature and pressure, RTP. Its temperature at 25 degrees Celsius and pressure 750.06 millimeters per mercury. So we are saying that the volume occupied by the 1 mole of a gas at standard temperature and pressure, it varies depending on this, because temperatures at STP and at RTP are different. So because they are different, even the volumes they do change. So this table, we need to know it very well, and we know the conversions. Just if you know that volume in decimeter cubed at STP of the gas is 22.4, volume in decimeter cubed at RTP is 24 decimeter cubed. So what you need to know is the conversion. converting this into liters, converting this into cubic centimeters, and also doing the same here, converting 24 in liters and 24 in cubic centimeter. So that's why we have this note that 1 decimeter cubed is equal to 1000 cubic centimeters, which is also equal to 1 liter. That is the conversion that they have used here to get all these, to get this, to get this, to get this. If you know this, then you can know this by using the conversion. You can see 1 decimeter cubed is the same as 1 liter. That's why we are seeing here we have 24, we have 24. But 1 decimeter cubed is equal to 1000. So when you use this conversion, you can convert 24 decimeter cubed to centimeter cubed, and you will be able to get 24,000 cubic centimeters. So this is the table that we shall be using when we are calculating, relating the moles of a gas with its volume at different conditions. At STP, we have at STP, and also we have at LTP. And you can see that at STP, it is a different volume compared to at LTP. So let's see how best we can approach some of these questions here. We have an example. Let's look at this example. So I think that what is the volume of 2 moles of ammonia gas? You see, they want us to convert moles into volume. But they're saying what is the volume of 2 moles of ammonia gas at room temperature and pressure at LTP, at standard temperature and pressure, that is STP. Don't forget that 1 mole of any given gas occupies a different volume at different temperatures, at room temperature and also at standard temperature and pressure. So they have helped us and put it in here in the bracket, but we can have the other table in our mind and have it very well, understand it, so that at any point when they don't give you this clue, you can be able to do it by yourself. So we're saying that the molar mass, the molar volume, 24 decimeter cubed per mole. 1 mole occupies 24 decimeter cubed at room temperature. That is, per mole, it means 1 mole of a gas at room temperature occupies 22.4 decimeter cubed. So that is what we are meaning in this case. Maybe I can note it down here. Here we are saying that 1 mole of a gas occupies 24 decimeter cubed at RTP. So we have that. So this is the interpretation of this. That 1 mole, when we say 24 decimeter cubed per mole at RTP, they are saying that 1 mole of a gas occupies 24 decimeter cubed at RTP, which means on this case, they are saying, still that 1 mole of a gas occupies 22.4 decimeter cubed at STP. Where are they getting from? From our table that we have summarized up there. Please feel free to pause and then note down. Put these notes down, and then you'll be able to practice the questions which I'm going to leave for you to practice, and then you'll be able to share your findings in the comment section. Let's look at the solution. So we are going to find the volume of the 2 moles of ammonia at room temperature and at standard temperature and pressure. Part A. We are saying that 1 mole of ammonia gas occupies 24 decimeter cubed at room temperature and pressure. That is something that we saw at the beginning. Now the question is, if 1 mole of ammonia occupies this at RTP, what about the 2 moles of ammonia gas occupy what? So if 1 mole occupies this, it means that the 2 moles occupy 2 times 24. And when decimeter cubed at RTP, which when you multiply, you get 48 decimeter cubed at RTP, and you get all your scores. Then at STP, which is the standard temperature and pressure, you recall what changes is the volume. We say that 1 mole of ammonia occupies 22.4 decimeter cubed at STP. What about 2 moles of ammonia? It will be 2 times 22.4 decimeter cubed at STP. And when you multiply, you'll be able to get your 44.8 decimeter cubed at STP. As simple as that. So when you know the other table, you can do any other calculation relating with conversion of volume to moles or moles to volume. Now, assume they have given you this volume. Can't you convert into moles? That is your practice question. Start from answer and you go back and you see whether you'll be able to get 2 moles of ammonia. Finally, we have convert volume of a gas into its number of particles. Converting volume of a gas into its number of particles. So we have example that's saying calculate the number of molecules in 0.48 decimeter cubed of hydrogen gas. Okay, this is a good one. Now here they want us to calculate the number of molecules. You recall these are the particles that we are talking about. And we saw the relationship between particles and moles, where we say that 1 mole of a given substance, it consists of 6.02 times 10 to power 23 particles. But in this case, we have volume and we don't have moles. So which means our first step in this case is to determine the number of moles present here. After determining the number of moles, then you can convert moles into molecules. Are we there? Let's go straight to the solution. Step 1. We first convert volume into number of moles. Very good. That is a question I was trying to bring here. Can you convert this volume back to moles? And now here the question comes. We want to convert this volume into moles. How do we do that? We still use our statement where we are saying that 1 mole of a gas occupies a given volume at a given temperature. Now here they didn't specify for us, is it at room temperature or it is at STP? If they don't specify for you, then you choose the one you want. So for me, we have chosen at RTP. And we're saying that 24 decimeter cubed of hydrogen gas are occupied by 1 mole of hydrogen gas at room temperature and pressure. If 24 decimeter cubed are occupied by this, what about the 0.48 decimeter cubed? If this 24 is occupied by 1 mole, what about the 0.48? Which means 0.48 will be the 1 over 24, I was saying that, times 0.480 moles. I believe this is clear. After that, use a calculator and you get the number of moles, and there you get your mark. You recall in the question they want us to calculate the what? The molecules. So we haven't reached the answer. That's why we say go to step 2. Our step 2 is to convert the number of moles into number of particles. In this case, we said our particles are the molecules. Are we together there? Yes. Now, where do we start from? We said that 1 mole of any gas, of any substance, we said from Avogadro's constant, from Avogadro's number, we say that 1 mole of hydrogen of a substance, it contains these particles. But for us, we're looking at a substance which is hydrogen, and the particles we're looking at is molecules. So we're saying that 1 mole of hydrogen gas contains 6.02 times 10 to the power 23 molecules. Now let's look at this. What about the 0.02? These are the ones we have already gotten in our first step. So what about these molecules? If 1 mole contains these molecules, what about 0.2 moles? It will be 0.2 times this one times this. That's why we have this, but we eliminated. Let me put this 0.02. So we have 0.02. You can put it there, 0.02. So we have 0.02 times 6.02 times 10 to the power 23 molecules. So our answer, when you multiply very well, you'll be able to get 1.204 times 10 to the power 22 molecules, and therefore there are 1.204 times 1022 molecules in 0.48 decimeter cubed of hydrogen gas, and you underline your answer. Part B. Are you seeing part B? Part B, 288 cubic centimeters of ethene, all at room temperature and pressure. So they want you to calculate. If you check very well, what they want is to calculate the number of molecules in 288 cubic centimeters of ethene all at room temperature. I want you to try out this and you share your findings in the comment section. Say, now the number of molecules of 288 cubic centimeters of ethene is this at room temperature and pressure. So that one, I am waiting for your answers so that we can see whether we are following. Then I also have other practice questions on the work. Now these practice questions are covering all the work we have covered in this lesson. And we have 4 of them. I'll read them, you note them down, and you calculate them. Calculate the volume occupied by 18.0 times, okay, there is a times here, don't forget, times 10 to the power 22 molecules of chlorine gas at STP. Then we have calculate the volume of 11 grams of carbon dioxide at RTP. How many moles of molecules are there in 18 grams of hydrogen gas? And finally, calculate the number of particles in 0.05 moles of ammonia molecule. So these questions, we have looked at them in this session. If there is anything that is not clear, go back and you go through, and then you'll be able to calculate this and you share your findings in the comment section. I'll be waiting to see your answers in the comment section. If possible, you can write on a paper and you take a screenshot and you share your findings, that even other people, they can always learn. We are saying don't forget to like. If this content that we are sharing, I'm sharing each and every time, is working for you, if it has worked for you at one point, please don't forget to like, and also comment and subscribe for more. And if it has not, please don't worry, no issues. And you can call on this for any inquiries, and or email on this number for any inquiries. You can share, and we see how best we can enjoy the beauty of chemistry. Otherwise, have a blessed time. God bless.